Today we will learn 2 group CX disconnection, in that the third type is 1,3 difunctional compounds. 1,3 disconnection approach is applicable to 1,3 difunctionalized compounds. Presence of two functional groups are at 1 and 3 positions to each other. A number of biologically active molecules possess 1,3 functional group, and this disconnection approach finds its applications in drug design and synthesis. We denote this disconnection as 1,3 disconnection. So in this disconnection, if you find two function groups which are at a position of 1 and 3 with respect to each other, then we can easily go ahead with the 1,3 disconnection. Example 1. One can see the 1,3 disconnection approach for the synthesis of 1,3 functionalized compounds. These compounds can be disconnected only at the carbonyl oxidation level, where unsaturated compounds are reagents for synthons. This is an example of Michael reaction. These reactions are effective for carbonyl compounds, cyanides, nitro compounds, and most nucleophiles. So let us take this example. So here, first, there is a carbonyl compound. See, 1,3 functional compounds are, first of all, very much applicable for carbonyl compounds. So let us start numbering the target molecule. So we give carbon number 1 for the carbonyl carbon, and then 2 and 3 for the adjacent carbons. And then we're going to disconnect at C3 and the nucleophile. So this disconnection becomes 1,3 disconnection, because we're going to disconnect between C3 and the nucleophile. Now, once we disconnect, we're going to write down as 1,3 DIX for above the retrosynthetic arrow, and then we're going to write down the synthons. The synthons is going to be Nu minus and the cation. Now this cation, there is a terminal cation, carbocation, which is present at the terminal carbon. Now this is a sp2 hybridized carbon. That means that there are two more hydrogens which are linked to this carbocation. Now what happens is, there's going to be a base which is going to deprotonate this carbon. That's one of the H plus is going to be removed by a base, and then there's going to be subsequent formation of a double bond between the two carbon atoms. That is, this is going to give rise to an unsaturated compound. That is alpha beta unsaturated compound. Now the synthetic equivalents of this type, wherein there is a nucleophile and there is a synthetic equivalent which is an electron rich compound, or alpha beta unsaturated compound, alkenes. So when you find this kind of an intermediate, or when you find this kind of a synthetic equivalent, then this is a typical example for Michael reaction. So usually 1,3 DIX always gives rise to Michael reaction whenever we write down the synthesis for this kind of disconnections. So first of all, let us study what is Michael reaction. See, in Michael reaction, it is beneficial for organic synthesis because it is used for the formation of carbon-carbon bonds. First, we have a ketone here. Let us see the mechanism. We have a ketone, and in presence of a base, it is going to abstract the proton at carbon 2. Once it abstracts the proton at carbon 2, there is going to be formation of an enolate. That is, an anion is formed at carbon 2, which you can see here. An enolate forms at the carbon atom 2. Then we have this carbanion, or also this is the nucleophile, is going to attack this electron rich carbon. That is, here we have taken it as the alpha beta unsaturated compound. So that is, the anion nucleophile attacks the carbon 3 of the alpha beta unsaturated compound. So once it attacks, or once it attacks that group, that is the carbon 3, then there's a bond formed between C2 and C3, which you can see subsequently. Now after this, what happens is, the double bond forms a carbanion on carbon 4. Now there's a carbanion which is formed on carbon 4, and this carbanion is going to abstract proton from the base. That is, it's going to abstract H plus from the base, and because of which we're going to get a 1,5 diketone of this kind. So here you can clearly see that there's a bond formed between C2 and 3. So hence this reaction is used for formation of CC bonds. Now let us go back to this equation, example 1. So here also you can see the same type of reaction, that is Michael reaction, is going to take place in these kind of examples, that is 1,3 disconnection. See here what happens is there is the synthetic equivalence is going to be NuH and it is going to be a ketone, an unsaturated ketone. That is nothing but alpha beta unsaturated ketone is going to be formed here as these two synthetic equivalents. So a synthetic equivalent of this kind is always going to give rise to the Michael reaction. So now here you can see the same kind of reaction taking place as I explained in that example for Michael reaction. Here also the NuH is going to, Nu minus base is going to abstract the proton from NuH to give rise to Nu minus, and Nu minus is going to attack at this terminal carbon of the alpha beta unsaturated compound, and then there's going to be the formation of a target molecule like this. So this is the reaction for 1,3 difunctional compounds. So for 1,3 difunctional compounds, students, we have to remember 2 to 3 hints for this kind of reaction. The first hint is always first look at the functional groups. If the two functional groups are at a position of 1 and 3 with respect to each other, then this is one hint for 1,3 difunctional compounds. The second hint is that when there are nucleophilic centers in the target molecules such as carbonyl, cyanide, then nitro compounds or carboxylic acids and so on, wherever there is electron rich, wherever there is nucleophilic centers in the target molecule, then this example becomes then this is a typical example for the 1,3 disconnection. So these two factors, if you remember and keep in mind, then definitely you can go ahead for writing these kind of retrosynthetic equations. Okay, now let's move on with the example number 2. So here we have amines. These are amines as the target molecule. Amines can be made by reduction of cyanides and these in turn by the Michael reaction. Base catalysis is required in this synthesis as OR minus is a better nucleophile than ROH. Now let us look at the target molecule. So here we have a amine in the terminal position of this target molecule. See, now we know that cyanides can easily be reduced to form amines. So hence what we're going to do is, the next step what we're going to write down is the functional group interconversion. We're going to interconvert amine to cyano. That is, this since it is in the retrosynthetic, we are going to write down as reduction below the retrosynthetic arrow and write down as functional group interconversion. So FGI reduction is going to be the main criteria for this kind of, for the first step of disconnection. Next, once we disconnect, we're going to get cyanide group as the intermediate, or this is the kind of the second step in the disconnection. Now here you can observe that the number of carbon atoms between NH2 and OR is 3, right? You can see count the number of carbon atoms between NH2 and OR is 3 carbon atoms, but after the reduction we are going to give, it is going to give rise to 2 carbon atoms. So there's only 2 carbon atoms between NH2 and between CN and OR. So this is why we're writing as 2 carbon atom is because we know that cyanide group on reduction is going to give us CH2NH2. So hence whenever you come across examples like this wherein there is cyanoamine and amine we're going to interconvert to cyanide group, make sure that you're reducing 1 carbon atom, that is 3 carbon atoms becomes 2, 4 carbon atoms becomes 3, 5 carbon atoms becomes 4. So like this you should remember, because CN on reduction gives rise to CH2NH2. So that's why we are going to step down the carbon atoms, that is from 4 or from 3. If there are 3 carbon atoms, we're going to write down as 2 after the disconnection. Now after this step what we're going to write down is, let's start numbering the carbon atoms. See, now first let us just look at this molecule. Now in this molecule we know there are 2 function groups, CN and OR, and these 2 are situated at 1,3 positions with respect to each other. That's first criteria. The second criteria is we have an nucleophilic center here in the molecule, that is the cyanide group. So hence we can easily write down the Michael reaction as the synthesis for this kind of disconnection. So before that, let us start writing down let us number this molecule. So cyanide gets carbon number 1, numbering as 1, and the carbon 2 and carbon 3 is what we're going to write down subsequently. Then we're going to disconnect between C3 and OR because this is 1,3 disconnection. So after disconnecting between C3 and OR, we're going to write down the retrosynthetic arrow, and above that kindly mention 1,3 disconnection, 1,3 DIX. Once we write down the disconnection, the next step is going to be writing down the synthon. So when we write down the synthon, it's going to be OR minus, and we are going to get a cationic synthon. So once we write down these 2 synthons, Next, we're going to write down the synthetic equivalent. So the synthetic equivalent is going to be ROH, and we're going to get cyanoethene as the synthetic equivalents. Now, here also you can observe that there is a nucleophile OR and there is a unsaturated system. There is an alkene here which is linked to a nucleophilic group. So that is cyano group. So hence what happens is, that's the reason what happens is we are going to write down the synthesis similar to Michael reaction. That is, we're going to write down ROH plus cyanoethene in presence of a base is going to give rise to the amine as a target molecule. So this kind of reactions will be, the writing down the synthesis is going to be just similar as the Michael reaction. Now let us take another example, example 3. 1,3 amino ethers can easily be synthesized by taking the help of 1,3 disconnection approaches. So the target molecule here is 1,3 amino ethers. So now what we have to do is, first, since there is a presence of amine group, let us first interconvert it to cyanide group. So write down as FGI, above the retrosynthetic arrow, below that write down as reduction, and we're going to write down the subsequent cyano compound here. And now let us count the number of carbon atoms between amine and oxygen. There are 3. So after the oxidation, it's going to be give rise to 2 carbon atoms. So 3 carbon atoms becomes 2 carbon atoms, because we know that cyanide group on reduction is going to give us 1 carbon atom extra. That is, it is going to give us CH2NH2. Cn on reduction gives rise to CH2NH2. That is why when you're writing the reverse of that, we write down as NH2 giving rise to Cn. That is, 3 carbon atoms is going to give rise to 2 carbon atoms. So that's why from 3 we're going to write down as 2 carbon atoms and then give the functional group. Now, look at the example. This is, look at the molecule. It's an example for 1,3 disconnection. We have cyanide group and also we have an oxygen group at the position 3. So hence we can do the 1,3 disconnection. Start numbering the carbon atoms 1, 2, 3, and then there's going to be disconnection at the C3 and oxygen. And after the retrosynthetic arrow, mention as 1,3 disconnection. Now, when we write down let's write on the synthons. The synthons is going to be a phenoxide ion and it is going to be an cyanoethane cation. So these two are going to be the synthons, and their synthetic equivalence is going to be a phenol and cyanoethene as the synthetic equivalents. Now once we write down the synthetic equivalents, next step is we have a nucleophile and we have also phenoxide nucleophile, and also we have an alkene, electron-rich compound, which is an alkene. So these two combines to give the Michael reaction. So the synthesis is going to follow Michael reaction. So now let's write down the synthesis. We have alcohol, so we have the phenol and cyanoethane, and we have cyanoethane. And in presence of a base like sodium methoxide, base is first going to deprotonate the phenol to give rise to phenoxide ion. Phenoxide ion is going to attack at the terminal carbon atom, that is this double bond, and then the double bond is going to shift. There's an electron pair between these two. It's going to shift to form the carb anion. Once it forms carb anion, from the base, the other group is going to be deprotonated. Again, I'm going to explain. See, first is we have a phenol and we have the cyanoethane. Right? A base is going to deprotonate the phenol. So once it deprotonates phenol, it's going to give rise to phenoxide ion, that is O having a minus charge. Now this is a nucleophile. The nucleophile is going to attack the alkane. It's going to attack this position at the carbon atom. Once it attacks, there's going to be a bond formed between those two, that is the oxygen and the terminal carbon atom. Subsequently, what is going to happen with the double bond, that is going to form a carb anion. Now once it forms a carb anion, there is going to be this hydrogen from the phenol which was left out, that is going to form a bond between the carbanion and the proton. So once it forms the bond, it is going to form a cyano compound. Now this cyano compound on reduction is going to give us the amine group. That is the target molecule. So this is how we're going to write down the synthesis and retrosynthesis for 1,3 difunctional compounds. Let us take another example. So here we have an acetol which is linked to the bromide, And see here, the first disconnection is going to be 1, 1 disconnection. See here in 1, 1 disconnection, we studied that whenever there are two function groups which are attached to a same carbon, then it follows 1, 1 disconnection. So now here we have the central carbon atom which is attached to two oxygen groups. So hence we are going to conduct the 1, 1 disconnection for this target molecule, that is the acetol. Then we're going to write down as acetol below the retrosynthetic arrow. Once the disconnection is conducted, it is going to give rise to an bromoketone. And this, when you look at this ketone group, it is again another example for 1,3 disconnection, because you can see here that bromine and the carbonyl group are at the position or between are at 1,3 positions with respect to each other. And hence, this is, we can conduct the 1,3 disconnection for this particular molecule as well. So start numbering. Carbonyl carbon gets 1 and 2 and 3 carbon. We're going to number as that. And then there's going to be disconnection between C3 and bromide group. So once there is disconnection between C3 bromide group, we're going to write down the synthons. Synthons is going to be the bromide ion and alpha beta unsaturated compound. So now we have a nucleophile, we have an alpha beta unsaturated compound, that is electron rich center. So now hence we're going to write down as the Michael reaction as the synthesis for this. So the Michael reaction is nothing but we're going to take up HBr. This alpha beta unsaturated compound with HBr is going to form the bromoketone, which on reaction with diol is going to give rise to the target molecule, that is the acetol. So this is how we're going to write down the synthesis and retrosynthesis. Next, we're going to study another example. See, in this example, we have a sulfur, which is at the position 3 with respect to the carbonyl compound. Now, again, let us start numbering. So we give 1, 2, 3 numbering to the target molecule, and then we're going to disconnect between C3 and sulfur. So we're going to do the 1,3 disconnection. Kindly write down 1,3 disconnection above the retrosynthetic arrow. And this is going to give rise to the synthons, a cation and the anion. Now what happens is the cation group, again after losing a proton, is going to form an unsaturated system. That is, it's going to form alpha beta unsaturated compound, and it is going to give rise to the two synthetic equivalents. Now we are going to use these two synthetic equivalents in presence of base OH minus is going to give rise to the target molecule. So here I've written down the equation, I've written down the mechanism here for the synthesis. First is a base deprotonates the SH to give rise to S minus group. So S minus group is going to attack on this carbonyl, it's going to attack on this carbon, that is the alpha beta unsaturated carbon, terminal carbon. And then there's going to be the movement of the electron between the double bond to form the carb anion. And after this, there is going to form, this carb anion is going to abstract the proton. That's why I've written here H plus. There is this carb anion is going to abstract the proton, and then it's going to abstract the proton, and then we are going to write down the final target molecule. So this carb anion, once it abstracts proton, will not be in this anionic form anymore. That is because it has formed a bond between hydrogen, H plus, and hence we're going to get the target molecule. So all this synthesis is following the Michael reaction. So whenever students, whenever you come across this kind of an example wherein there is two function groups and they are 1, 3 positions with respect to each other, and there is a nucleophilic center like a nitro, carbonyl, cyano, acid, and so on, and there is a heteroatom like an oxygen or sulfur or nitrogen at third position in the target molecule. Like this, for example, we have a sulfur here, right? At the third position, there's a sulfur. So in place of sulfur, if there's nitrogen or if there's oxygen. So all these criteria will give rise to 1,3 disconnection. So these are the hints for you to recognize 1,3 disconnection. See, only 1,3 disconnection, there is Michael reaction. So this is another differentiation between all the other disconnections that we have studied so far. So I hope this video was clear to all of you. Thank you very much.